Hello. So we're going to be looking at energy. That's what Chapter 7 is about. Work, energy, simple machines. It's got a lot in it. So let's get started. So we're going to be looking at different types of energy, but first of all, we're going to look at the definition of work. So let's go look at work. Work is force times distance. Now, we've already talked about impulse, which was force times time. This is force times a distance. So you're pushing on something, maybe pushing on your car, trying to get it to go, and you're pushing for a certain distance. You've done work on that car. And so down below, there's the picture of the lawnmower, right? Somebody is doing work. And as he pushes that lawnmower, and so he would be having force times distance. And as long as it actually works, then you can have what's called a network. So we'll talk about that too. So as long as it goes somewhere. Now, the units of this, we have a new unit. It's called a joule. And so when you have work is force times distance, then that's newtons times meters. And a newton is a kilogram meter per second squared. When you multiply by a meter, then it just comes out to kilograms meter squared over second squared. And that's the definition of a joule. Okay, so 1 joule is 1 kilogram meters squared over second squared. Now, often when we're calculating work, people don't want to go to joules. They often just stop at Newton meters. They say, that's a good unit. We'll just use Newton meters. So that's another possibility also. You can just use Newton meters. Okay, let's look at a little deeper into this. So the work is the product of force exerted on an object and the distance the object moves. Now, one of the things is that the force and the object have to be in the same direction. So it doesn't count if the object moves perpendicular to the force. That force did not create the motion of the object. You have to create work with a force that succeeds in moving the object. So here we've got someone pushing on a lawnmower again. And the thing is, when you're pushing on the lawnmower, you're pushing down along the handles usually, right? That's your net force that you're pushing on it with. But the force that actually counts here is the component of that force that is in the direction that the lawnmower is moving. So the lawnmower moves across the ground, the horizontal. So we only want to count a horizontal component of that force. And so let's say that she pushes the lawnmower for 20 meters. That would be the distance. And let's say that she was using 15 newtons of force. And so we would just multiply those. And so you would have 300 Newton meters or joules. Now, sometimes you're picking up some object. So the force you're using is upwards against the force of gravity. And so here we've got this weightlifter picking up around 100 kilograms. He's got 4 25-kilogram weights there. So that's the mass. That's the mass, but that's not the force he's using. The force is equal to the weight of the barbell. So the weight of the barbell, remember, would be mg. So weight, and here we have to be careful because now we've got a lot of W's running around. We've got weight and we've got work. And so in this case, I'm talking about weight. So that's often why this book spells things out. Weight is going to be mg. And so in this case, that would be 100 kilograms times 10 meters per second squared. So we're going to get 100 times 10, which is going to be 1,000 newtons. Okay, so be careful. If a formula is asking for the weight, then you must make sure it's mg, not just m. And so the work that he does, he lifted that up. Maybe he lifted it from the ground. So that's probably about 2 meters. And so the weight would be 1,000 newtons times 2 meters. And so that's going to be 2,000 joules. Okay, but we also could get it through a formula for when we're lifting up an object. We can just get it from mgh, the weight, mg, times the height, h. And so that's another way to get this whenever you're lifting something up, and what we call potential energy. That formula is mgh. And so yes, we could have just not calculated the weight in advance. We could have done mgh, and that would have been 100 times 10 times 2 meters. And so, yeah, it would be 2,000 joules also. Okay, here is this convict pushing against a brick wall. And you do no work. Is that correct, right? Because the wall isn't moving. Remember the force, he's pushing with his hands this direction, but the wall isn't moving. So is he doing any work? Is he doing any work on the wall? Is he doing any work at all? Well, the wall's not moving, so the wall has no work. But he may actually be doing a little bit of work with his muscles, because he's straightening his muscles as he pushes on the wall. And so inside his body, the muscles are doing work. They're just not succeeding in pushing the wall down. And so there's the exercise of isometrics, where you don't move, you just push, and that will actually increase your muscles because you are lengthening them, stretching them over and over again. Now, what work can do is it changes the amount of energy in an object. So we're going to be talking about energy in a moment. We'll be looking at this slide again later. The idea is that you can do both a positive work or a negative work. So like positive work will add energy. So you push on a box or a couch or something, and you're adding energy to it, making it go. But negative work would be like a brake, when you're slowing something down. Well, in that case, you're removing energy. So we'll be looking at this more later when we look at the work energy theorem. Okay, now, so work will change the amount of energy in an object. What is energy? Energy can be defined in a couple of ways, but in this book, one of the definitions is that which can produce a change in matter. So light energy can heat matter. Sound can vibrate. Hammers can smash things to pieces. Bulldozers shove things, and springs pull. So all of those are showing some sort of energy. You're changing the situation or the matter itself. And the thing is, when you see energy happening is when it's being transferred or transformed. So you transfer it from one place or one object to another. And so I can throw a ball, right? And usually I would, but what happens is I'm taking the ball, which was still, and then I'm throwing it, giving it a type of energy of motion. And so I transferred energy into the ball. But energy also gets transformed from one form to another. So the ball was, the energy that I gave the ball was motion, but that energy started out from me, from the food that I ate. So it's chemically stored energy. So anyway, so let's look at different types of energy. But remember that energy will get transferred from one place or object to another. It will get transformed from one form to another. Okay, so here's some types of energy. What we call potential energy is a type of stored energy. So it's also sort of an energy of position. And so when you are pulling on a spring, you are storing energy in it. So, so here's a little spring coil. And by squishing it, I'm putting energy into it. So then it can push my fingers up afterwards, right? So a spring can store energy by its position, by the shape that it's in. And then gravitational, you lift something up, you're giving it gravitational energy. And so those are some types of potential energy. Kinetic energy is the energy of motion. Anything that's in motion, whether it's atoms vibrating or a spaceship off in space moving along, so a rocket, those are all types of energy. Your car, your bike, anything around you that's moving has kinetic energy. Electromagnetic energy is the energy that comes in light or electromagnetic waves. And so there's visible light, but there's also X-rays, radio waves, ultraviolet rays, microwaves, gamma waves, infrared waves, and just plain solar radiation is a combination of the types of rays that come from the sun, mostly visible. And so anyway, you've got many different types of electromagnetic waves. And for short, you can write EM for electromagnetic. And you know that energy is coming, the sun, from the sun. The sunlight warms the sidewalk, warms your face. You have received energy from the sun. Okay, there's chemical and biologically stored energy, which would be energy that might be stored in chemical bonds. So like you burn gasoline or burn oil or burn wood, what you're doing is releasing energy from those chemical bonds. So wood, coal, oil, sugars, fats, a chemical battery, those are all stored chemical energy. Okay, now you can also have electrical energy. So that's usually a lot of times what people think of energy. So lightning, current, voltage. And then nuclear energy. So the idea is that for nuclear energy, that the core, the atom has a nucleus that stores energy, that has energy stored in it. And that's why a nuclear power plant works, is the energy is released when some of the energy is released when you change the nucleus of an atom. Okay, I threw dark energy in here kind of for fun. I don't know if we'll get time to ever talk about that, but dark energy is believed to be almost 70% of the energy of the whole universe. And so 70% of the energy may be this form of energy called dark energy, but we haven't quite figured that out yet. But if it's true, then that's a pretty incredible amount of energy. It's called dark, though, because we can't really see it well. We're having to sense it through gravitational fields and things like that. Okay, so lots of different types of energy. And so this picture is fun because you can see that we have kinetic energy from the motion of the atoms in the tornado. We've got some electrical energy here. And there's a radio tower here, so we've got radio waves or microwaves coming out. So that's electromagnetic energy. So heat energy, kinetic energy, as heat energy, and electrical and electromagnetic. Okay, let's go look at stored energy. Okay, so let's look at potential energy. Now what this woman, this incredible woman, has done is she is able to pull a bow with her foot and balance on her hands, as you can see. What a great, strong woman. Anyway, so I understand she can even hit the bullseye of a target. So anyway, but what has she done here? She's pulled the string of the bow and pulled it back, and that means that she has stored energy into it. And then when she releases that string, it will push the arrow forward and transfer the energy to the arrow. But right now it's in the stored position, in the tension of the string and the tension of the bow. Okay, so let's look at this potential energy. So again, stored energy. And the thing is, energy has the potential for doing work. What does that mean? Well, imagine if you lifted up a rock. The higher you lift it, the more potential energy you give it. And then, you could drop the rock. And you could drop it onto a nail and drive that nail into some wood. This is basically what you're doing with a hammer. You lift the hammer up, you give it potential energy, and then you allow it to fall and drive the nail in. Now, when you drive the nail in, there's a force and the distance that it goes into the wood. So you're doing work. And this is how pile drivers work. This is how when you're hammering something, it works. You're taking potential energy that's gravitational and turning it into work. So anyway, so you can imagine a drawn bow, of course. Same thing, you're storing the energy in the bow. Now that stretchiness, we call sometimes that spring potential energy. And we often call potential energy, we put PE, because it's hard to write potential energy all the time. So spring potential energy is when you have something that's bent and has tension in it. So it could be a rubber band, right? But then there is gravitational potential energy, and that's when you lift something up. And since gravitational is a large word, we sometimes put GPE, gravitational potential energy. And so you can raise the ram of a pile driver, put that bowling ball on the closet shelf, put some water behind a dam. The water behind the dam has potential energy. When it goes down through the pipes in the dam to where the generators are, the turbines, then what it does is it turns that potential energy into kinetic energy and into eventually electrical energy. So there's a sequence of potential energy, kinetic energy, and finally electrical energy, which then can go to light somebody's house and turn it into light energy. So anyway, so yeah, there's this conversion of energy from one type to another all the time around us. Okay, now gravitational potential energy, we already covered the idea of work when you lift something up. So when you lift something up, the force that you have to use is the weight of the object. That's how much force you need. And the height, of course, is how high you raise it up. So what happens is that you get a formula for potential energy, gravitational potential energy, equal to that formula of work that we talked about earlier. So gravitational potential energy is equal to mgh. So that's the formula mgh that you're going to use for calculating gravitational potential energies. Okay, so here is a bowling ball. We're going to raise it up, and we're going to raise it up 3 meters. It's 1 kilogram in mass. So how much potential energy are we giving it? Well, we just put it in. The mass is 1 kilogram. G is 10 meters per second squared, and the height is 3 meters. So you put that together, and we've got 30 watts. Well, you can see you could get your kilograms meters squared over seconds squared here, and that, of course, is a joule, right? That's supposed to be a J. Now, the interesting thing is, it doesn't matter how the ball gets up to that height. It just matters that it is at that height. So these balls are all at 3 meters. They're all 1 kilogram balls, which is a 10 Newton ball, right? So a 10 Newton ball is 1 kilogram. And they've been raised up in different ways. One was raised straight up to the top of the post. Another one went up a ramp. Another one went up some stairs. And you could even have one that kind of goes up and then goes way too high and then eventually ends up back at the right height. The thing is, their energy, when they're finally at rest, is GPE. So the gravitational potential energy. So it's all MGH. So they all have the same energy no matter how they got there. It's their potential energy that we care about. And that just depends on the height. Right? And the height for all of these is 3 meters. They're all in the same place. Okay, now what about kinetic energy? Kinetic energy is that energy of motion. And the formula for kinetic energy is 1/2 mv squared. So m is for mass, v is for velocity. So of course you can use speed because we won't always have a direction connected with it. Now, when you play around with those units, mass is kilograms, and meters per second, well, that is the velocity. So you square it. Those units end up being the same as we saw for gravitational potential energy, and for work, they come out in joules. So work, gravitational potential energy, kinetic energy, all types of energy basically have the same units that you can use, which is joules. Now, sometimes we call energy the ability to do work. So can kinetic energy do work? Well, you can imagine throwing something that knocks a can off a shelf, or you get a toy car moving, right? We often will throw a ball and hit something and make it move. We have done work in that case. Anyway, it's a pretty simple formula. Here we've got this runner. And so let's say that he was a 60 kilogram person. And let's say he's running at 5 meters per second. Well, you just would throw that in there. Kinetic energy, 1/2 mv squared, 1/2 of 60 times 5 squared. Okay, so pretty easy to throw things into the formula. You don't have to worry about mass versus weight. You definitely want to use mass in this formula also. And so 5 squared is 25. 1/2 of 60 is 30. So what would I end up with? I'd end up with 30 times 25. And so that would be 750 joules. Okay, let's go look at another problem. Okay, so just again, here's a bicyclist. She's rolling along at 5 meters per second also. Okay, and so very similar to what we just did. So what is her kinetic energy? Kinetic energy, 1/2 mv squared, 1/2 of 80 times the velocity, square it. So we get 1/2 of 80 times 5 squared is 25, 40 times 25, and we would end up with 1,000. Okay, now let's say that she increases her speed to 10 meters per second. Okay, so the mass stays the same. But what will happen now? Okay, so figuring out her kinetic energy now. And now we have half of 80, but now we've got 10 squared. And so her energy is going to turn out to be 4,000 joules. Okay, now her speed doubled, but her energy is 4 times as much. And this is one of the things that happens for in kinetic energy. Because the formula has the square of the velocity, then as you change the velocity, you get big changes in energy for smaller changes in velocity. So again, like here we doubled the velocity, but because it gets squared, that's 4 times more energy than we had before. What would happen if we tripled her velocity? What if she was able to go to 15 meters per second? That'd be about 30 miles per hour, so you'd have to be pretty good. Well, then what would happen is that if that was the case, that would actually make 9 times as much energy as she had before. This is one reason that baseball players get paid a lot for being able to throw a ball 100 miles per hour. A lot of people can throw a ball 50, 60, 70, but getting the energy to throw the ball that last 20 to 30 miles per hour, you need so much more energy because think about it. Someone who can throw at 50, someone who can throw at 100 miles per hour. Doubling the speed means 4 times as much energy. So the pitcher has to be able to push the energy into the ball. And how they do that? By greater force, by a longer distance that they throw. Force times distance, that's work. That's how you get the energy into the ball. But how do you get 4 times more energy? Anyway, that's why they get paid more. It's not something everybody can do. Okay, and that's the end of this portion. So we're going to go on to part 2, conservation of energy.